So thank you for the proposed question. Now I would like to take the audience here on an amazing adventure into the phenomenon of branching light. So today, this will be our special itinerary describing the amazing journey into the mysterious branching effect, starting with a little experimental demonstration setup, followed by a qualitative and quantitative exploration, combined with numerical model results generated along with a final leap into the bigger wave picture. So without further ado, let us begin. We start off with an experimental setup involving the use of a simple laser pointer, a cup, and adjustable phone stand. But due to the COVID pandemic, I'm not able to access my university's laboratory involving the use of a microscope, lens, and certainly an RGB interferometer to measure light intensities. Nevertheless, this was not an essential requirement, given that I was able to produce equally successful light experimental results of the branching pattern even without a microscope, as you will see later. From the previous schematic setup, this will be what will be seen in the physical setup, where the basic procedure experimentally will be to add detergent soap into a separate container or water along with some optional teaspoon sugar to stabilize the bubble form a little longer if you like. Dip your hand into the soap solution, and after which you, due to the possible curvature of the bubble film arising from surface tension, place the laser pointer at a sufficient distance for the laser light port to be a bit diffuse to achieve higher probability of light rays parallel to the cup's top while still aiming at the cup's top. And after careful adjustment of the laser pointer in achieving a very low angle of incidence, we see that the laser light from the video does indeed branch out very clearly, visible to the naked eye as you would perform in a lab using an interference microscope and optical fiber from previous research work. So the recorded video results demonstrate strong experimental evidence that the branching effect can be done at the convenience of your own home. Previous attempts involved trying optical fiber, a particle cap to form a bubble film, but they were very unsuccessful due to the fact that there was significant bright light, which makes it very unstable. So as you can see here, these were the most successful results, where further work was done to actually extend this in terms of how do we want to design a medium to illustrate this effect of producing specific patterns. However, macroscopically, there was no visible difference that can be seen here. So therefore, I would expect that there would be a microscopic difference, but due to experimental limitations, we are not able to see this very well. So what exactly is happening here? Well, we want to look at the qualitative theory first. So in this case, what you're seeing here is that when you talk about light waves will propagate in the vacuum as a TEM wave at the speed of light. But vacuum isn't the interest here. We want to be interested in the soap film where wave is propagating. And what interestingly soap film does is that it's acting as a waveguide that is constantly modifying the boundary conditions that these light waves are being propagated into. And this leads to changes in phase velocity. And if we extend this further into the N effective refractive index, where it's expressed as C vacuum and C film, we will be able to notice that these changes in N effective will lead to the change in direction of the light that's propagated in our branching pattern. So if we go deeper into this potential landscape, our N effective can be mapped out across the two-dimensional landscape. And this is important because it actually depends on the film's thickness. As you can see on the top right corner, you can see that there's thin films interference where different light of different colors are being exhibited. And because different colors are being exhibited, different wavelengths are being present at different spatial points within the soap film. And for that reason, this will actually help give us a deduction that this corresponds to changes in the thickness of the film and therefore leads to weakly changes in refractive index in the soap film. So from these two understanding from that N effective has spatial fluctuations and light propagation in waveguide, we deduce two fundamental principles that leads to the branching pattern. One being that the disordered medium has random variations in your N effective, and second, that the wave must propagate through that same medium that has this feature. So I wanted to introduce you this classical quick drift model where on the top left, you see a homogeneous medium where there are three distinct RGB lines. Now, if I apply run this code each continuous times, I will be applying a distortion to this medium in a series of black dots. And you notice that the RGB lines are being distorted along with the series of black dots that are in tandem with each other. And if you constantly do this several times, what you're going to see is on the bottom right, where the light actually changes in a very disordered and very chaotic manner in terms of the directions, as what you will obtain in the random potential of many rapid random fluctuations in this random potential landscape. So that is the intuitive model we can get a sensing for our branching light pattern. But obviously we want to go deeper into this and look into a much more quantitative model. And first, we want to start this by a mathematical consideration of your monochromatic optical wave frequency, angular frequency that propagates through this slat waveguide of your soap film. And as you can see, we want to look at the wave function of this, which is at the core of the branching pattern that is happening here. So to do this, we want to simplify this model in the most rational possible way. So as you can see from our previous experimental setup, our laser light ray is being directed to the soap film such that it is at a very angle that's very, very close to zero. So what this parallax approximation is trying to tell you that angle theta between the wave vector and the optical axis is made very, very, very small for this parallax approximation to work. And basically, this notion, if you translate to our idea of waves, is basically trying to tell you that the diffraction effects of the wave is becoming very minimal in compared to the distance that the light rays are being propagated through this medium. And therefore, when we do the mathematics, knowing that the wave function only depends on your spatial point of x, and after that, doing a little bit of mathematics, we get this very complicated parallaxal Helmholtz equation in the orange box. But that is not the most important part here, because we are going to run this equation into our mathematical simulation. But to do this, we need to create a random potential. And in this random potential, we create this random potential that is based on two important parameters. One is the smoothness and variation of the refractive index, and second being a peak-to-peak amplitude of the, in terms of the maximum fluctuation of the randomness in this potential. So after we do this, we plug the Helmholtz equation into the computer simulation that will produce the various branching patterns based on this random potential. So numerical models, as you can see from our intensity scale, the peak-to-peak amplitude is first varied while keeping the smoothness and variation constant. And as you can see, as this peak-to-peak amplitude increases, your angular spread increases with a few branches that happens at the very bottom, as you can see. But if we keep the peak-to-peak amplitude constant with a change in the length scale, which basically means that it's not very smooth for the length scale variation being 10, we see that yes, the angular spread is there, but the number of branches actually increases much more, where they are as represented by the numerous number of small streaks, as you can see. And lastly, if you try to run the same code for the same algorithm many times, each branching pattern will appear different. And this will agree with experimental what in the video, that the branching pattern is a dynamic phenomenon, but that changes with the potential landscape. Of course, I was unable to produce this to examine this microscopically because due to experimental limitations. But I think with access to the university lab, I think I'll be able to verify the correspondence. But now, fortunately for you, the story doesn't end here, because now we are going to apply these two essential principles to examine other wave phenomenon that is relevant to from our optics investigation. And we begin this with tsunami waves on the right. So if you look at this, we must first ask ourselves, what is the disorder potential here? Well, it is actually the barometry, or the height of the ocean floor with the sea level. And then we look at what is the wave propagated here. So obviously it's our tsunami waves, and in our Helmholtz equation that we reduce from shallow water equation, your barometry is has the randomness that is evident in this model. And that is what is going to lead you to on the left diagram, where the branching pattern is modified, is shown manifested in two ways. One is that tsunami waves are changed in direction, and the other being that the height of the tsunami wave profile is varying. And that's not all. We try to use it for matter waves, it's also the same effect. So again, we ask ourselves, what is the disordered potential? So in this case, is our gallium arsenic 2 degrees of freedom for our gases, and that will produce very random ripples in background potential, which affects the potential energy of the electron, which is our matter waves that's being propagated here. So finally, and we apply that for sound waves. Unfortunately, I've not found an experimental visualization of this model, but we can still rationalize that this branching pattern still happens because first, again, our disordered medium, which is our fluid that's of interest here. And second is that in our Helmholtz equation, when we simplify, we see that the wave has inherently the adiabatic compressibility that is also have this randomness in our disordered fluid. Finally, a summary of our key ideas is that one, we mentioned this important point is that there must be a disordered potential that has able to display weak changes in this refractive index. Second, wave that's being propagated through that medium of that we are interested in. And we applied these principles to the other wave phenomena that actually shows that there is branching effect that is being made evident here. And finally, our numerical simulation results macroscopically agrees with what the parallax Helmholtz equation would produce, as you will see in our experimental results from a basic simple model that you can be done at the convenience of your home. And with these ideas that I'd like to bring you across, I would like to end this presentation, and I hope you enjoyed the journey into the branching effect phenomenon. Thank you.
Start when it's convenient for you.
Good afternoon. My name is Oleg Bashtenko, and now I will be a reporter on task number 13, branching light. According to the statement of the problem, a reporter should to analyze the phenomenon when laser beam, while passing through a thin film, it branches on branches and investigate this phenomenon, qualitative and quantitative analyze this effect, and analyze different phenomena on the wave structures, on another wave structures. In this report, reporter firstly showed us the principal experimental setup. We think that such experimental setup was clearly showed for us. We agree with this experimental setup, and then reporter goes to qualitative explanation of this effect. And this is, we think, that will be very big improvement of this report when if the reporter showed us different inhomogeneities that can provide this effect. For example, it may be self-focusing of the beam, for example, heating of the light, heating of the film, or light pressure, or it can be inhomogeneities of the structure of the film. For example, different thickness of the film may produce such a branching. We want to see some proof of this mechanism of phenomenon. But we think that it will be really improvement of this report. Also, we want to talk about the explanation of non-uniform distribution of reflective index. As reporter said, he didn't analyze this in his report, but we think that it's very important part of this task, and we think that analysis of such a phenomena will slightly improve this report. Next, in next part, reporter showed us theoretical model when he wrote Helmholtz equation with random distribution of reflective index. We think that for such an explanation of the phenomena, this model is good. However, there is questions about the proof of the theoretical model that reporter chosen. After that, we saw the analogy between this phenomenon that we observe in the experiments of reporter and between the quantum case. The reporter modeled the random potential and passed light through this potential, and we saw similar pictures, but we saw these similar pictures only using our eyes. We think that in experiment and in theoretical, there wasn't analyzed different parameters of branching light. For example, number of branches on different cross sections. For example, thickness of light beam. We think that analyzing of quantitative parameters in this task will really improve the phenomenon. Also, we want to speak about, we want to talk about influence of different parameters in this report. For example, using different materials for making film, different liquids. For example, using different different lasers with different wavelengths. Does it maybe changes the shape of the structure? So we think that it was the main improvement of this report. So we propose such discussion topics, and I want to start with the mechanism of the reflection coefficient difference in this task. Is it really only that was shown in the report, or maybe different any mechanism may influence on the picture?
All right. So we need to understand that this difference in the refraction, as I mentioned, the refractive index, is because there is a change in the film thickness, as I mentioned. And what's interesting that perhaps I didn't make it very clear is that obviously the soap bubble is going to pop eventually, right? The soap bubble doesn't last permanently forever. Eventually, after a while, the soap bubble will pop. So as this happens, that happens is because when in the soap film, the water is evaporating, and the film is going to get thinner and thinner as less water content is being buried. So at this point, if you look at it closely, there will be actually sharp fluctuations in terms of how the refractive index. It will be much more discontinuous as less water is present, and therefore the film overall gets thinner. And I want to mention that you also brought up an interesting point about this heating effect that is present by the laser that shine through the soap film. So there could be a possibility of heating, if that's correct. From the Ukraine side, I just want to verify there's a heating component, right?
Okay, I want to say that to prove your mechanism, we need to compare your theoretical and experimental results. We can't compare it, only use our naked eye. I think we should analyze different quantitative parameters. For example, number of branches in these pictures. So when we analyze number of branches in the theory and experiment, we can predict the mechanism and compare. Maybe your mechanism was it doesn't
okay. I understand your concerns, and your concerns are valid. So that is why I did mention importantly that microscopically from numerical models, as I mentioned, that the length scale variation of the smoothing variation will produce much more branches, and that is an important feature which I identified, having how many branches that are present in a certain area and how many branches can compare that with an experimental. However, as I mentioned, due to the experimental limitations, I'm not able to examine the branching pattern in a very microscopic way. So if I was able to do this microscopically, I will first look at as what you mentioned, the number of branches within a certain area occupied by a certain area. And that is exactly what I want to investigate, because on the same level, on the same concern they mentioned, that is how I wanted to vary the medium in terms of how, like adding, let's say, more soap, adding a different kind of substance in it, like a sugar solid, would change the parameters that I've analyzed, which is your smoothness in variation, as well as your peak-to-peak amplitude. So yes, this is I acknowledge this experimental limitation, but yeah, this is what, yes, it is a problematic area for now.
Our second question, third question maybe, about different parameters of film, of soap, and of laser. What do you think about it? Maybe it will improve your reports when you use different soaps with different structures of the film. Maybe the composition of the soap really affect on the shape of branches. What do you think?
Okay, thank you so much for your question. So I answered the first part on the concentration of soap. So obviously I tried to change the concentration. So as you have seen earlier, that I tried to triple the concentration from 10% to 30%. So macroscopically, as I mentioned, you can't see a difference. But what I could say is that if you understand the formation of how a soap bubble forms, the lower the concentration of the soap, the thicker the film that is initially formed when you start off, when I did the soap film formation. The soap film will start off being very thick when you start off with a high water concentration. But with a higher soap concentration, your soap film begins initially to be very thin. So that's going to definitely affect the branching pattern, and it's going to affect how disordered in terms of, because the film is very thin, so the fluctuations in terms of thickness becomes much more frequent and much more rapid. That's one. And obviously, experimental limitations is hard to see this, but that's why I mentioned extension work. I want to do this. In terms of parameters of lasers, yes. So you mentioned something about this interesting idea of wavelength. So for wavelength, that's a very interesting question. Is that if I were to instead use not green light, I use red light instead, and I shine red light into the same disordered medium. So what would I observe in the branching pattern? So that's an interesting question, is that you would agree with me that red light has a longer wavelength. Is that correct?
I think yes.
So, yes. So on that basis, if I use this theory called, I'm not so sure you heard of it, it's called Cauchy's dispersion relation, which expresses the refractive index for a specific light of a certain wavelength, and is related by a very basic idea of a constant plus 1 over lambda squared. If I make this lambda very large, your refractive index for that particular light will be less, will be closer to 1. So for that reason, the angular spread of, let's say, the light or having longer wavelength will be less. And I would expect for your case of wavelength, which is a good consideration, is that the branching angular spread will be less. So as for intensity wise, the intensity was also an important consideration because when I did this experiment, I tried to put the laser really, really close to the soap film. And the interesting result was that the branching effect wasn't exactly very obvious for two fundamental reasons. One, experimentally, is that the effect is too bright, so it's a bit masked the effect of the branching. So that's not very easy to record in the video. And second, it is better to put at a sufficiently far distance so the intensity is less and your branching effect for angle adjustment is better. Yeah, I hope that answers the question.
Okay, and my question about how can you, in your numerical modeling of this process, how you can change these parameters that you can change in experiment, how we can compare your prediction, because I still can't understand, was your mechanism proved in your report or not? I can't compare your theoretical and experimental results. It depends on different parameters. Maybe your theoretical prediction predict the result of the experiments only using one soap or only using one numerical simulations. How we can check it?
So the quick answer is unfortunately no, because that will require us to actually measure the thickness profile of the film, which can be done if we have proper instrument to do interferometry and measure the thickness of the film over position, and from that we can map up the effective refractive index exactly and pass that into our simulation to generate a prediction. However, this is problematic in our case for two reasons. First is that we do not have the instrument. To do that, we will need interference microscope and we need high-speed cameras because the film is actually fluctuating quite quickly. So to capture that, the capture speed must be really high, and it's way beyond what we can do given that we have been in the lockdown situation for like more than half a year. And then additionally, another reason why getting a direct quantitative comparison is extremely difficult has also to do with these fluctuations as well. The film is always fluctuating and the fluctuation is very quick. So even if we map out the profile at one instant, if we take the microscope away and look at the branching pattern will be different from before because the film would have changed over the time where we have taken away the instrument and started the laser. So those are all the complications which make it difficult to do a direct comparison. And in fact, in the literature, we have not seen any direct comparison yet. The most we have seen in literature for people who are actually doing this experiment with per instrument are qualitative comparisons. So I think the best we can do in this scenario is compare things qualitatively and show that the factor we have identified can indeed lead to branching, while we cannot negate the possibility that there could be other effects contributing to the branching.
Okay.
So that's our opinion.
We have nearly same directed to question. It is about the thickness of the film. As I understand, to define the actual shape of the film, you have to use a very good camera with good resolution. Do I correctly understand you?
Yes.
Okay, however, in your theory, as I understand, you do not have it, and in your theory, you use the random distribution of the refractive index. And what is the reason of use of such a model? You may use some kind of random distribution of not of local change of the refractive index, however, some kind of lines with a random distribution of them, or some regions. In which range did you change the refraction index? How have you chosen such values, and how can you compare it with the experiment?
Well, so unfortunately, we cannot do direct experiment comparison because we do not have an instrument to measure the film. That's a built-in problem and we can't get away with that, unfortunately. So for the theory, we have just picked the simplest way to generate a random potential. So basically we have a grid and then we generate a random effective refractive index on the grid point and interpolate and smooth it. And that's how we generate the random potential. This is the simplest way. And we tried that as a proof of concept to show that given this random potential from some source in some way, the branching can happen. And in fact, the branching is not very dependent on how this potential looks like. So it can happen like across a very wide range of parameters we use in the generation of the random potential.
Okay, thank you very much.
Alexander here, I think. So my question is first for the reporter and then for the opponent. What is your estimation of a special scale of inhomogeneity in your optical qualities of your film? Like millimeter, nanometer, what it is?
Okay, I will answer the question first. So for the soap film thickness, my understanding is from estimation and doing a bit of research work, it varies about 10 to about 10,000, not 10 to 1,000 nanometers. So for that range in thickness for the soap film, I would say that in terms of micrometers, yeah, so that will be roughly the variation it is. Although I would have to admit that it would change a lot more as the soap bubble continues to sustain nearing the end of its longevity because it will evaporate.
Okay, we do not have a lot of time, so the same question for the opponent. Do you agree or do you have other estimation?
No, our estimation gave nearly 10 micrometers. It was a inhomogeneity of the distribution of inside the film. Yeah.
Okay, thank you very much.
Thank you, Alexander, for questions. Alberto, please.
So I have a question for the opponent team. So you multiple times you came on the point of the number of branches. And I would like to ask you, how do you exactly define the number of branches in a continuous system such as the soap?
Yes, it indeed is a really interesting question because it is indeed hard to define it. However, by the intensity, like we can define it by some kind of border intensity, lower which we do not consider something as a branch. Upper this border, we consider something to be a branch, and also according to the width. Like if the width also maybe it is lower than the width of the beam initially, or twice of it, we can consider this as a beam.
Okay, and how would you measure that?
By the photo analysis. For example, in the photos which presented the reporter, we can make a photo analysis of this in the cross-section of the beam. In the cross-section of its propagation, we can define the intensity distribution, and from it we can find that.
Thank you. Okay, I will ask also a quick question to the reporter team. So, do you think this phenomena happens in not on the same order of magnitude, but does it even happen very slightly in water?
So meaning to say that just to clarify, shining the laser into just purely water, is that right?
Yeah, like from the tap.
I would say that it probably wouldn't because like although okay in the tap there's many composition, there's changing composition like other stuff, but I would say it wouldn't because I think the surfactant molecules provided by the soap film is extremely important, which provides the waveguide, which basically modifies your boundary conditions, which is an essential requirement for your to elucidate the two fundamental principles that I've discussed, which is how they produce the randomness in the potential. So yeah, I would think that for your case, the fluctuation might be a bit small.
Okay, thank you. That'd be all for me.
Thank you, Alberto. Okay.
Yes, so I would like to ask first the reporter and the opponent. You said that you were limited in your experimental resources. What additional equipment would you have needed if you wanted to measure the width of the film and the correlation length of the inhomogeneities?
Thank you for your question. So as I mentioned, if I had the opportunity to access the university's laboratory, I would want to use an interference microscope. So basically using microscopy techniques as outlined by previous research work, which is the fundamental mode to measure thin film interference and the specific microscopic patterns of your branching. so I can compare this well with my numerical models. So yeah.
Okay, and the opponent, what's the simplest possible way for measuring these quantities?
To measure thickness, the reporter can use some kind of a source of white light, using which he can, from the interference picture, define the distribution of the thickness in the subfilm.
Mm-hmm. Thank you.
Thank you. Okay. Does other jury members have some questions? Jürgen, please.
To the reporter about the analogy of the tsunami waves and branching there, can you comment on the ratio between wavelength and subfilm and to the other tsunami thing?
Okay, so sorry, I just checked. To compare the wave slide for basically tsunami waves, is that correct? In terms of order of magnitude.
So you have the wavelength of laser and subfilm in your experiment, and you have the tsunami waves or deep of sea and other thing. Can you compare how they both situations are related to?
For the tsunami waves, I would feel that the random variation is on a larger scale than the wavelength, because the tsunami waves height profile will be in the order of 10 to 100 meters. And for your subfilm and your light waves, so obviously light waves will be in nanometers, so your subfilm will be a few millimeters thick. So I would say that the correlation length should be comparable to your wavelength in both cases, which is separate.
Okay, good afternoon.